In this video, I'm going to demonstrate how to do simple regression using the data and example from Cengage Now question 1. In this problem, we want to know how winning percentage for a given season affects hot dogs sold for a randomly chosen game within that season. And the data are summarized in the table below. So I'm going to go ahead and copy the data to Excel. Now the first thing I'm going to do is I'm going to put the X in column A and the Y in column B. I'm going to flip row 2 to row 1. I'm going to do a little formatting so we can see the data better. Now the reason why I did that is because when you highlight data to scatterplot it, the first column Excel assumes are X values. The second column Excel assumes are Y values. So you have to kind of flip those. So to make a chart of how this relationship looks in a scatter plot, click on Insert, Scatter, click the one without any lines, and you can see that it looks like a upward sloping relationship. I'm going to delete that thing, and I'm going to format this so that the minimum value on the y-axis is what looks like about 70,000, right? So I'm going to format the axis. I'm going to choose 70,000 as my lowest y value. And I'm going to do the same thing for X, where it looks like the lowest value for X is probably 20. I'll just put in 20. And then I'm going to close out. Okay, now you can see it a little better, can't you? So the next thing we need to do, I'm going to kind of shrink this up a little bit so it's easier to see in the screenshot. I'm going to right click. I'm going to put my cursor over a data point. I'm going to right click. I'm going to add a trend line. I'm also going to display the equation on the chart. I'm going to display the R-square value on the chart as well. Hit close. So Y, which is hot dogs sold, I can actually literally change that to H, and then I got 1307.2 times X, but that's winning percentage, right? And then I got this down here. This is the intercept. So that's the intercept, and this is the slope, and this is the R square. And I'm going to maybe make it a little bigger so we can see it better. I'm going to also get rid of the grid lines so we can see a relationship. So this line here, this black line, is the graph of this equation. If hot dogs sold is solely explained by winning percentage, then theoretically you could use simple regression, which is what we use in this Cengage Now problem. In simple regression, the regression model is the equation that describes how the observed values of y relate to the independent variable and error term. So right here is the error term, which cannot be known, which is why we use a Greek letter E, epsilon. The slope, beta 1, which we cannot know, which is why we use beta. And the true intercept, which we cannot know, which is why we use beta again. The regression equation is the equation that describes how the mean value of y, denoted E of y, which stands for the expected value of y, is related to the independent variable x1. One of the regression model assumptions is that the mean of the errors is 0. So when you add up these errors, you get 0. When you divide by the population size, you get 0 divided by capital N, which is 0. So the expected value of the error is 0. And that's why epsilon is missing in this equation. The estimated regression equation is the equation that describes how the predicted value of y is related to the independent variable. Now notice that we use b0 and b1 here. We don't use beta 0 and beta 1 anymore. And the reason why that is because we've taken sample data. In this case, we have 5 observations. We've taken sample data and we've used Excel to estimate the values of beta 0 and beta 1. The estimate of beta 0 in our example here is 35,534. If the sampling is random, then we expect this value to be near the true value, which we can never know, beta 0. So B0 is 35,534, which is an estimate of beta 0. We cannot know beta 1. If our sampling is random and our sample size is large, then we expect the slope here, the estimate here, 1,307.2, to be close to the true value of the slope, beta 1, which again cannot be known. So B1, 1307.2, is an estimate of beta 1. B0, 35,534, is an estimate of beta 0. So B0 and B1 are like X bar and S, and beta 0 and beta 1 are like sigma and mu. Back to Cengage Now, question 1. Part A says, use Excel to estimate B0 and B1 to 2 decimals. In our chart, we have 1 decimal for the B1 and 0 decimals for the B0. So what we're going to do here is we're going to actually conduct a regression analysis. This is the chart version of it, which has very limited information. We're going to do the full regression, which is going to be presented in a table. And the way you do that is you go to Data, Data Analysis, scroll through until you see Regression, and you want to click here and then push this button to load your Y values. When you load your Y values, you want to include the label hot dog sold and then the 5 hot dog values below it. Then you do the same thing for the X range. You click on that white area, click on that button, include the label and the 5 observations below it. Because we've included the labels, we need to click Labels. I like to put the output right below the table, or right below the data. Now when you click output, you got to click this white area because for some reason Excel will put you up here. So when you click output range, click that white area. I also like to get the residuals whenever I do a regression. So I have output range, labels, and residuals all clicked. I click the white area, I click this button here, and I'm going to put the output right there. And then I'm going to hit OK. Now I'm going to do a little cleaning here. I'm going to reduce the number of decimal places to maybe 3. So I highlight all of these numbers with lots of decimal places. I'm going to reduce the number of decimal places to, say, 3. And I'm going to do that same thing down here. Okay. I'm also going to get rid of this part of the table. Okay. So notice that we have what is called R squared in our chart. That value is identical to the R square in the regression summary table, 0.811. The standard error of the regression is just over 4,335. The phrase standard error shows up in the regression summary table. It also shows up in the coefficient table. These standard errors are the standard errors of these coefficients. So you can think of these as x bars, and these are the standard errors that are associated with these x bars from a Chapter 9 one-mean test. And then the t-stats are just the ratios of these two values. If I divide this number by that number, I get t-stat. If I divide this number by that number, I get t-stat. And these are the p-values that are associated with this t-stat. These are, by the way, two-tailed p-values. And you can compare these to an alpha from a two-tailed null hypothesis test. The F statistic is interesting. In simple regression, it is simply the square of the coefficient test statistic. So if I square the coefficients test statistic, I get the F stat, which is interesting. And the F stat is used to test for model significance. The T stat is used to test for coefficient significance. And because there's only one x variable in here, that one x variable comprises the model. So when you do a coefficient test in simple regression, you're doing the model test because there's only one independent variable. Notice that the p-value of the f-stat is the same as the p-value of the t-stat. Again, for that same reason. The model comprises one independent variable, winning percentage. So the t-test of coefficient significance is equivalent to the model test in simple regression. Now we have all the information we need to answer the questions from Cengage Now. I'm going to go ahead and reduce these to 2 decimal places, and I'm going to copy the estimate for beta 0, known as B0. I'm going to copy that into Cengage Now. I'm going to copy it there, and I'm going to copy it here. So I've copied the estimate of beta 0 into this box for B0, and then in this box for the intercept. I'm going to do the same thing with winning percentage. I'm going to copy that value and paste it into B1, and this B1 is the estimate for beta 1. Because it is the estimate for beta 1, it is the slope of this equation. This equation looks very similar to the one in Excel, in the chart. Let's see if I can get this on one screen. Okay, so I got y hat. Remember, y hat denotes the predicted value of y. In this case, predicted hot dog sales. It equals the intercept, which is identical to this number here, which is only to 0 decimal places, plus the slope times x. In this case, x is winning percentage. So that equation there and this equation here are equivalent. Now in part B, we want to enter the following information. The coefficient of determination is the r square. And we can get it from the chart, or we can get it from the regression summary statistics table. And r square, the coefficient of determination, to 3 decimals is 0.811 in my problem. The standard error of the regression is found in that same table. Excel calls it the standard error, but it's actually the standard error of the regression. I want to reduce this to 2 decimal places. Then I'm going to paste it right here, standard of the regression. The residual degrees of freedom are found in the ANOVA table of the regression output. So I have degrees of freedom in this column. I have the regression degrees of freedom, residual degrees of freedom, and total degrees of freedom. The residual degrees of freedom are 3. Why is that? Well, we had 5 observations, and we've estimated 2 parameters, beta 0 and beta 1. 5 minus 2 is 3. The estimated coefficient of the regression model is that value. This is the estimated intercept. This is the estimated coefficient. Don't let that confuse you. So the slope shows up 3 places. The estimated slope shows up these 3 places in our problem. The standard error of the regression, the standard error of the coefficient is the value that is just to the right of the estimated coefficient. In part C, we're going to conduct the test of coefficient significance using 2% significance. The null hypothesis is beta 1 equals 0. The alternative hypothesis is beta 1 less than or greater than 0. Because the significance level is 0.02, and this is a two-tailed test, we divide the significance level alpha by 2, so in this case 0.01, and that is the column of the t-table. We had 5 observations, and we estimated 2 parameters, beta 0 and beta 1, so the degrees of freedom are 3. So we're in row 3 of the t-table. So when you go to row 3 of the t-table and you're in column 0.01, the critical value is 4.541. So we have a negative 4.541 and a positive 4.541. And we have 2 critical values because we have a two-tailed null hypothesis test. The t-stat, remember, is just the estimated coefficient, B1, divided by its standard error. Those values are right here. So 1307.24 and 364.19. If I take this B1, the estimate for beta 1, and divide by B1 standard error, I get a t statistic of 3.589. And since the t statistic is in the do not reject region, the null is not rejected at 2% significance. Using the p-value of the test statistic, 0.037, notice that 0.037 is bigger than the alpha level of 0.02. Because the p-value is bigger than the alpha level, what that says is the probability that if you draw a line straight up to here, and then over here you draw a line straight up from negative 3.589 to here, the area to the left of this value over here, and the area to the right of this value over here is the p-value, in this case 0.037. So when the p-value is big, as it is here, big relative to the alpha level, when the p-value is big, the t-statistic is close to 0. That is, the t-statistic is under the hump of the t-distribution, suggesting the coefficient is insignificant. So in other words, when the p-value is big, the t-stat is close to 0. When the t-stat is close to 0, it is inside its critical values. When the t-stat is inside its critical values, the estimated coefficient is said to be insignificant. Going back to Cengage now, we can now answer part C. The critical value is plus or minus 4.541, correct? That's from our table. Dividing the estimated coefficient by its standard error, we did that already, gave us 3.589. We're going to do that to 2 decimals, so this would be 59. The estimated coefficient's test statistic that appears in its regression table is 3.59 to 2 decimals. Because the null hypothesis for the test of coefficient significance is not rejected using my data, we can say winning percentage has no effect on hot dogs sold. The coefficient of determination, which was 0.811, can be converted to a percent by multiplying it by 100. So the coefficient of determination implies 81.1% of the variation in the y variable. In this case, the y variable is hot dogs sold. 81.1% of the variation in the y variable, hot dogs sold, is explained by the model. And in this case, the model is winning percentage. Now we're going to double check our work to see if we got all the questions right. And we did get all the questions right, which gives us a really nice warm feeling inside.